Alright, in this video we're going to talk about materials testing. You should have a couple things in front of you. Your notebook, a calculator might be helpful, your printout of your dog bone graph that I'm going to draw along with you. If you don't have that, that's back in Canvas. You'll see the link for that. Print that out for your notes. Anything that I would like you to write, I will specifically say so. You're going to see me skipping through some slides. Just take notes on the things that I mention. I'm also going to be talking a lot faster because you have the ability to pause, and please do so as you need to. If I'm talking faster, then you can write, which I probably will be. Okay, material testing. Let's get down these two definitions, static testing and dynamic testing. Basically, as you can see, static testing, it's response to constant loading, and that's what our tester is going to be doing. Dynamic testing, just like it says, this first sentence is perfect. Material response to varying loading, cycling, like pulling and releasing, or pushing and releasing. Ours is just going to be static testing. The reason we do this, all kinds of reasons. The best example I can think of is a bike helmet. You know, don't bike helmet companies want to know how much force that helmet can withstand if there's an accident? Same thing with cars, car bumpers. That's why we're doing this testing. We're going to be testing with what's called a dog bone. It actually looks like a dog bone. It's kind of skinny in the middle and larger on both ends. Our tester looks a lot similar to this one on the right. Both of them accomplish the same thing. They're grabbing this piece of metal and they're ripping it apart. This one just has jaws. This one you can see has threads that screws in, and it pulls that steel apart until it breaks. And it spits out a graph. The printer spits out a graph, and from that data we can determine certain things about that material. Let's see. Go ahead and jot down this graph real quick. Your graph for your dog bone and most dog bone graphs look really similar. We have a force on the y-axis. This is a lowercase delta, and it looks like an unfinished 8 when you're writing it down. That's the best way to write it. It's like an unfinished 8. And this is elongation, so this would be 0, and this would be whatever distance from 0, however amount that dog bone's stretched. So basically what happens is we're applying force, and as soon as I apply force, obviously this material is going to stretch, and then it really stretches here, and then it breaks off right there. That's what you're looking at. And you could title that you know, example dog bone graph. All right, a couple equations. Let's go ahead and write down let's write down this little sentence. Stress is load per unit area. Stress is load per unit area. The equation is load over area, or the way you'll most commonly see it written is down here where my mouse is, and that is your lowercase, which one is that? That's your lowercase sigma, and then force over area. Also worth noting, let's a little refresher of how we find area. That's pi r squared. And let's do this example right here. 430 pounds of force. And there's our area. And that particular sample had a stress of 35,000 psi. For a lot of these calculations, you're going to see that the numbers are pretty high. You know, we are talking about steel. Okay, next one is going to be strain. And let's see. Here's a great definition. Let's do this one right here. Strain, the amount of stretch per unit length. That funny looking E is our lowercase epsilon. So I would write down this sentence and both of these equations. Here's our lowercase delta again. That represents the amount of stretch, and L sub O is just our original length. And let's go ahead and do this example. 0.0625 inches over 1 inch of original length, and we have a strain of 0.0625. Normally we would cancel these units. A lot of times you'll see the answer actually written as inches per inch. And if you think about it, this sample stretched 0.0625 inches per every inch of material. All right. A couple more things. We're going to talk about elastic range and proportional limit in just a second. Here we go. I believe this is your last equation. Modulus of elasticity, and that is abbreviated with just a big capital E. The proportional constant ratio of stress and strain. And that's our equation, stress divided by strain. And let's see here. We'll get to all that stuff in a second. Let me just double check a couple things. Last thing, let's talk about ductility, this word. And this first sentence is perfect. Amount of plasticity before fracture. Some materials are more ductile than others. As you're writing, look up at this animation as it starts over again. The material in the middle will go through a process called necking. That's where it gets slender in the middle. And this particular material, or this simulation, you can see it has a lot of ductility because of the way it broke. It's almost like, imagine bubble gum. You're going to pull, it's going to stretch, and then it will finally break. Please make 3 quick sketches in your notebook. And this one would be the most ductile, and then this one would be the least ductile, and this one's kind of in between. Those atoms on these two are desperately trying to hold together before the very last moment, and they broke. This one it was very rigid. You can tell by the way it broke, like breaking a cracker or a cookie. Okay, switch over to your graph, and I think I might do a separate video for that.